In this video, we're going to talk about the Poisson process. You might have seen it, of course, in Stat 230, but we're going to have a little bit more formality when we talk about it this time. First of all, we start off by defining a counting process, which is a continuous time but discrete state space stochastic process that has the following conditions. First of all, it has to be integer valued, so n of t is an integer for all t. Second of all, it has to be non-negative, so n of t is greater than or equal to 0 for all values of t. It's non-decreasing, so it can never go down. If t is greater than s, then n of t is greater than or equal to n of s. And finally, we interpret n of t minus n of s as the number of events that occur in the time period from s to t. Notice the closed bracket after the t, if t is less than s. So because of that, we can interpret n of t minus n of 0 as the total number of events that occur by time t. For example, the world population would not be considered a counting process, but the total number of people that have ever been born is a counting process. See if you can think about why those two things, which sound very similar, are different. Why one is a counting process and one is not. The reason is that the world population could go up or down at any time. So it doesn't satisfy the third condition of being non-decreasing. But if we keep track of the number of people that have ever been born, that is going to be non-decreasing. So basically, again, a counting process is something that's going to count up the number of events that occur over time, and it's never going to go down. An event cannot unoccur. Then we want to talk about two specific conditions that happen in a Poisson process. First of all, we have the idea of independent increments. We call n of t minus n of s, where t is greater than s, an increment, so a number of events in a particular period of this process. And we say that n of t, as t is greater than 0, the process, has independent increments if and only if non-overlapping increments are independent from each other. In other words, here's a time diagram. If we have time 0 here and sometimes s, t, u, and v, then the number of events that occur in that period, which would be n of t minus n of s, and the number of events in that second period, n of v minus n of u, must be independent of each other. So n of t minus n of s is independent of n of v minus n of u for all possible choices of s, t, u, and v that satisfy those inequalities. Logically, the interpretation is basically just that the number of events that happened yesterday can't affect the number of events that happen today. So if we have non-overlapping periods, there's no influence of one event over the other. We always want to critically evaluate whether the assumptions that we're making are going to actually hold in reality whenever we're using a statistical model like this. So for example, if we had a model for the number of traffic accidents at a particular intersection, you wouldn't really expect there to be dependence under normal circumstances between two non-overlapping periods. If there were dependence, that would mean someone is keeping score. Someone is looking and saying, there haven't been a lot of accidents at this intersection this week. Maybe I'll make some the next week. Now, obviously, we know that doesn't happen. There's not some evil traffic controller in a room pressing a button to make the lights all turn green at the same time. But under normal circumstances, again, you wouldn't expect the process to remember how many accidents there were last week and have that influence the number that there are this week. In some situations, of course, this assumption could be violated. You could even make the argument that if there were a lot of accidents last week, maybe people will be more aware and more careful this week. So you could argue that there might be dependence in that case. But under normal circumstances, independence might be reasonable for a lot of situations. And again, it just depends on the situation. You want to critically evaluate whether you think those assumptions will actually hold in real life. The next thing I want to talk about is called stationary increments. So similarly, we're considering an increment, which is n of t minus n of s, where t is greater than s, and we say that the process n of t has stationary increments if and only if the interval n of t minus n of s only depends on the length of that interval t minus s. So it doesn't depend on when it's happening, only on how long it is. And that length of that interval is t minus s. So in terms of a picture here, if we have S1 and S1 plus t, and then S2 and S2 plus t, the number of events in those two periods, n of S1 plus t minus n of S1, and n of S2 plus t minus n of S2, those must have the same distribution, because those intervals are the same length. They're in different places in this process, but since the intervals are the same length, they have to have the same distribution. Now, I'm not saying they have to have the same value. It's not saying that the same number of events needs to occur in both of those intervals. That would be a violation of independence. What I mean is that it has the same distribution. So it has the same probabilities of taking on each of its possible values. You may well have a different number of events in those two periods, but they have the same distribution. So logically, the interpretation of this is just that the events in this process are happening according to some kind of constant rate. So we don't have periods of high activity and periods of low activity that are systematic throughout this. So you wouldn't allow a process that has higher activity during the day and lower activity at night. That would be a violation of stationary increments. And this assumption is often violated, particularly over long periods of time. If you think about the number of births, that's going to change based on, fertility rates over periods of centuries. But for short periods of time, it's usually pretty reasonable. So again, it's always a good idea to think about whether the assumptions you're making will hold for the time period that you're considering. If you're thinking about cars passing through an intersection, obviously there's going to be higher activity during rush hour and lower activity in the middle of the night. But if you're just talking about observing it for a couple of hours, then maybe stationary increments does make sense. So it just depends on the context. All right, with all of that in mind, we're now ready to formally define a Poisson process. We say a Poisson process, again we'll call it n of t, where t is a real number that's positive, is a counting process that has 4 additional conditions. First of all, we have to start at 0, n of 0 equals 0. Second of all, we need stationary and independent increments, both of those. Then, if we want to look at the probability of one event happening in a short period of time, from t to t plus h, that's going to be lambda h plus little o of h, where little o of h is basically just an error term that goes to 0 faster than h goes to 0. And lastly, we need the probability of 2 or more events in that same short interval to be little o of h. In terms of logic, that essentially tells us that no 2 events can happen at the exact same time, because as h goes to 0, that probability goes to 0. So with all of these conditions, we can actually prove that n of t, the number of events that have happened by time t, has a Poisson distribution with parameter lambda times t. There's a ton of different ways to prove this. You can prove it using a differential equation, which is what's done in the Stat 230 course notes actually, or in our course notes, it's done using the limit of a binomial distribution as h goes to 0. So you can check out those proofs if you like. You don't need to know them for this course, but what the interesting thing is that any number of events by time t is going to be a Poisson distribution. And it also means that the increment, the number of events between time s and time t, is Poisson with parameter lambda times t minus s. And that's true for all t greater than s. We might also be interested in the inter-event times in this process, and that's the time in between events occur. We know already that if we suppose an event has just occurred, and we let t be the time until the next event happens, we already found that t is going to have an exponential distribution with parameter lambda. We did that way back in chapter 1. So if we're going to define ti to be the time in between the I minus first and the ith events, then we can also know that the ti's are going to be independent and identically distributed exponential random variables. We know that they're identically distributed exponential random variables because this process has a constant rate, and we know they're independent because of the independence of the increments. Independence of the process, which is also sometimes known as the memorylessness of the process, the Poisson process itself has no memory of what happened in the past, tells us that those inter-event waiting times are going to be independently distributed. So how long you waited for the last event isn't going to influence how long you wait for the next event. This is different than the memoryless property of the exponential itself. This is saying that the whole process has no memory. Also, if we let Sn be the total time until n events occur, so from time 0 all the way until the nth event, then Sn can be written as a sum of t1 through tn, which we know is a gamma distribution with parameters n and lambda. So this is pretty cool. We actually have 4 different ways of defining the Poisson process, and they're all equivalent. So we could say that n of t is Poisson with parameter lambda t for all t. We could say that all the inter-event times are IID exponential, or we could say that the total time until n events is gamma. And any one of those conditions can replace the last two conditions in the earlier definition that we had of the Poisson process. You might want to take a second and see if you can prove some of those equivalences. So you should be able to find any one of those definitions and use it to prove any of the others. It's kind of neat, and you can try that if you like, but you won't have to do it on a test or anything. So altogether, what a Poisson process looks like, we can see by plotting a sample trajectory or a sample path of this process. We can plot time on the x-axis, and that's going to be continuous, and the number of events on the y-axis, and that's going to be discrete. So at 0, we start at 0, and then at some point we'll jump up to 1, and then at some point we'll jump up to 2, etc. We'll keep going. Sometimes it might take a long time for an event to occur, sometimes it might take a very short time to occur. And then we can mark off what these quantities mean. Each of those times in between a jump is an inter-event waiting time. Those are independent and identically distributed exponentials. And then the total cumulative time to observe numbers of events, those are going to be our SNs, and those are those gamma distributions. So this is how the Poisson process looks and how we see the relationship between n of t, the ti's, and the SNs. Lastly, for this video, I'd like to look at an example. This is one of the ones from the back of the course notes. Suppose that we have a Poisson process with a rate of lambda equals 5 calls per minute. You can always tell something is a rate if it's given as a number of events per minute. So I want you to interpret in words and find the numerical value of the following things. P of n of 1 equals 3, P of n of 2 equals 3, P of n of 4 equals 3 given n of 2 equals 1, P of n of 4 equals 3 given n of 2 equals 1 and n of 1 equals 0. And finally, we're skipping E, we'll save that for the next video, P of T1 is greater than 1/3. Give that a try before you keep watching the video. See if you can write down what these mean and also calculate those values using what you know about the Poisson process. All right, for A, this would mean the probability of observing 3 calls in the first minute, or really any 1 minute period, but here just the first minute. We know that n of 1 is Poisson with parameter 5 times 1, and so we can calculate this probability and get 0.1404. For B, we're now looking at the probability of observing 3 calls, but in the first 2 minutes of this process. N of 2 is going to have a Poisson distribution with parameter 10 this time, 2 times 5, and so that gives us a probability of 0.00757. Now logically, I want you to think, why is this so much smaller than the value in part A? Well, remember, this process has an average of 5 calls per minute. So it's kind of reasonable to observe only 3 calls in 1 minute, but it would be pretty unusual to only have 3 calls in a 2-minute period. You would expect an average of 10, and 3 is way further outside the normal value that we would expect. So that's why this probability is so much lower. For part C, we're looking at the probability of observing 3 calls over the first 4 minutes, given that there was 1 call in the first 2 of those minutes. So we have 2 overlapping periods here. We have a 4-minute period and then the first 2 minutes of that. So if we draw a little diagram here, that's what it looks like. We know that there was 1 call in the first 2 minutes somewhere, and we want a total of 3 calls in the whole 4-minute period. And so that means we need to have 2 calls in that second period. So we can rewrite this statement in terms of a probability involving the increment. The number of events that happen between time 2 and time 4 is n of 4 minus n of 2. And since that's an increment, it's going to have a Poisson distribution with parameter 10. And we just want the probability of that equaling 2. So we plug that in and we get 0.00227. For D, the interpretation is the same as part C, but we're just also conditioning on the fact that n of 1 was equal to 0, which means there were no calls in the first minute. So we're looking for this probability given those 2 things. And the cool thing is that we can actually drop the condition. Why can we do this? Why can we say we don't care what happened by time 1 if we know what happened by time 2? This is the same idea as the Markov property. If we know what happened by time 2, any previous information is completely irrelevant because the process is memoryless, or those independent increments are at play. So the idea of independent increments in a Poisson process is the exact same interpretation as the Markov property from discrete time Markov chains. Finally, for f, we're looking for the probability that the time until the first call is greater than 1/3 of a minute, or 20 seconds if you want to think about it that way. So t1, the time until the first event, we know is exponential with parameter 5. So if we just want the probability it's greater than 1/3, we take 1 minus the CDF of the exponential, and that gives us 0.1889. But we could also rephrase this problem to think about the probability that n of 1/3 being equal to 0. N of 1/3 is the number of events that happen by time 1/3, and we want that to be 0. We want there to be no calls in the first 1/3 of a minute. And n of 1/3 is going to be a Poisson distribution with parameter 5 times 1/3, or 5/3. So then we can plug in the probability function of the Poisson and end up with the exact same result. So that gives you some idea of how to work with the basics of the Poisson process. In the next video, we'll look at some of the advanced properties. See you then!